Hello everyone, welcome to the GNOSIS Annual Conference for 2021. My name is Don Pollacco and I'm a co-PI for the network, and I'm going to give you a little introduction to GNOSIS. And we've also got an interview with one of the GNOSIS supporters, Lord Martin Rees, who I'm sure many of you have heard of. It's quite controversial, some of his views, which are good. So I'll just start now. I'll tell you a bit about GNOSIS. So GNOSIS is set up by STFC, which is the Science and Technology Facilities Research Council. And it's really to look after big telescopes and big facilities, but it contains some science like astrophysics, nuclear physics and particle physics. And these more blue skies type research, the idea here is that some of this research is actually applicable. So the idea of GNOSIS was to set up a network that could help researchers to apply their knowledge into some of the big challenges. And the challenge that GNOSIS addresses is to do with the debris population. In fact, it's migrated on, it's more general than that, more about the near Earth population of physics, etc. And also the real world application of its effect on space traffic. And it's there really to collaborate with industry, but also government. And we also have another aim, a political aim, and that is really to help raise the awareness of the debris problem, both within academia to try and bring more support into this area, but also at governmental level. And I think for one reason or another, all of these aims are actually coming to pass one way or another. So within STFC, so like I said, these are a bunch of astrophysicists and nuclear physicists and particle physicists. Well, there are many things within Astro which are obviously useful in terms of observational work. So I've listed a few of the observational techniques, things like polarimetry, spectroscopy, hyperspectral imaging, as you would probably know it as. Lots of moving object work, of course, but also things like fast imaging, fast light curves. But one of the great things in the UK Astro system has been surveys. It's been one of the strengths in the UK system for decades. And so we're really good at surveys, at all wavelengths, I should say, dealing with the data, the modeling and the statistics, and things like data mining of those results as well. And then there are obvious skills that are in this community, things like orbital analysis, light curve inversion, and then some of these more sophisticated modeling techniques. And I've just listed machine learning and neural nets, etc., which are widely applied. And then there's the less obvious thing, which is because everything in particles and astro are difficult to measure, then there's been a lot of instrument work in sort of novel detectors. So these kids are the kinetic induction devices, which are really good at energy resolution as well as spatial imaging, and a lot of work in lasers for things like adaptive optics imaging as well. So there's quite a big group of people that could be convinced to become more involved in the debris work. But there's also lots of other work going on in other research councils. So again, I've listed some of the things that I know about. There's a lot more things like population statistics, orbital analysis, re-entry analysis, conjunction analysis, much more applicable things that are going on usually within engineering departments and often funded by EPSRC. So the interesting thing is when you look at the research councils, this kind of falls in between the gaps. In STFC, there isn't really core science in STFC at all. But nonetheless, we've been successful in extracting funding to support this work, and even extracted time on major telescopes to do this work. So the main source of funding is UKSA, the Space Agency, and recently I'm pleased to see that the Space Agency has started offering short-term contracts specifically at LEO debris, for instance. And the UKSA has also administered things like the ESA contracts, and when we had the EU SSA contracts, those as well. But not so much of this finds its way into universities, I think mainly because it's quite applicable research rather than blue skies research. And so I think academics have needed a bit of convincing that this was actually exciting stuff to do. We all know that the Space Agency is interested in licensing, and that's really important. But also EPSRC has also started sponsoring some low-level space technology, low TRL technology. So a bit about GNOSIS then. So GNOSIS was set up in 2019. It's an STFC-funded network project. We've got a few more years to run. We've got two PIs, there's Bob in Edinburgh and myself at Warwick. We wrote the proposal. Gosh, we were young and naive then. The chair of our board is Catherine Courtney, who many of you will know. And we decided we would be different to other networks. We would have program managers, and these are people that I'm sure you all know, Dins and Stuart Eves. And these are people that are very much in touch with the commercial and military side of this area. And that was a deliberate choice so that we could connect into industry really easily. And that's been a great success. Our manager now is Teresa Harrison, and most of the work that you're seeing today is due to Teresa. So thanks, Teresa. I know it's been a nightmare. And the secretary is a recent PhD graduate, James Blake from Warwick. So this is well, I should say that over the last year or more, we've basically had a complete program. It's all been virtual, of course, and well, I don't know what you're like, but I've had enough of this virtual stuff. But in the future, we're moving towards a more hybrid program. There are real advantages to a virtual program, and you'll see some of the speakers in this conference have come from all over the world. And that couldn't be done in an ordinary conference setting. The network itself is there to promote collaboration and networking. So we don't have big lots of money, but we do have some bits of money. So we've already part funded a PhD student. We could do others. We can do small projects, proof of concepts. So we have all these money. And if you look on our website, you'll see the meetings and the discussions after meetings, and that's how you can access the funding. So now I just want to play you an interview recorded by James Blake, discussing with Lord Martin Rees on his views on this subject. So I'll just play it now.
It's my pleasure to introduce Martin Rees, who's the Astronomer Royal and also the co-founder of the Centre for the Study of Existential Risk at the University of Cambridge. So thank you very much for joining us, Martin, and welcome to this first GNOSIS Annual Conference. It's a pleasure to have you with us, at least virtually, to discuss space sustainability. And I'm sure a lot of the topics that we'll cover will crop up over the next couple of days as part of the conference. So I'd like to jump in, if I may, with our first question. That is, what in your opinion, is the major risk, if you like, associated with the growing activity in space?
Well, of course, the main figure is the number of spacecraft that are going to be in orbit. There are going to be about 100,000 in orbit by the end of the decade. And that's going to include 42,000 as part of the SpaceX Starlink project, and about 12,000 Chinese ones as well, etc., in addition to all the other efforts in space. And of course, we have several thousand spacecraft in orbit now, and more importantly, we have thousands of dead ones which are still in orbit. And I think the key concern, obviously, is that the more there are, the more risk there is of a collision. And of course, as we'll be hearing in the conference, there's a big concern that there could be a runaway effect, which could eventually make low Earth orbit unusable. So that's the most obvious concern. And so one needs to minimize the probability of collisions between spacecraft. And of course, there's another more scary possibility, which is that nations are talking about space weapons of warfare, weapons where you crash a spacecraft intentionally into another. The Chinese famously did a test of this kind of thing a few years ago, which led to a huge amount of debris. And we want to ensure that that sort of event doesn't happen again.
Yes, as you mentioned, Martin, the catalogue's getting even bigger by the day, and that's something that certainly with our space surveillance and tracking facilities, it's really becoming a strain on what we can actually achieve at the moment. So yeah, I would certainly agree with you there. So in your opinion, whose responsibility is it to keep space sustainable? And I guess we can split that into the past and also the future in terms of where that side of things is going.
Yes. Well, I think if we think of the Starlink project, which is run by SpaceX, I think it's clear that they are responsible, they're doing their best. And quite apart from the issue of collisions in the debris, as you probably know, there's concern among astronomers about the effect of all those spacecraft up there, because, of course, they can all be seen moving across the sky, and it's a detriment to certain kinds of astronomical observations, survey telescopes which are trying to look for variable objects, etc., are confused by these. And so the one benefit, in a sense, is that because they're in low orbit, you only detect them after dusk and before dawn, and so you have all night. But the Starlink people are aware of this, and they're trying to paint the spacecraft black and avoid reflecting surfaces, etc. So they're doing their best. But there's another issue which astronomers worry about from Starlink, which is more serious, and this is that the radio signals from all come down to Earth, and this is happening day and night. And so, although I'm not particularly clued up on this, this is something which I think radio astronomers and all other users of the radio bands are going to have to worry about. So that's one concern, and I think one has to engage with the large companies. Starlink is the largest, but there are other companies which are going to be launching large numbers. Another which is launching 7,000, Amazon launching 3,000, etc. So I think we've got to rely on the goodwill of those companies, which are at least run by people who at least understand the issues and the scientific importance. But of course, the more scary possibility is the intentional use of anti-satellite weapons, etc. Because of course, in high Earth orbit, we depend crucially on satellites, and they can be attacked. And I think one needs to ensure that there are the maximum kinds of legal constraints on this. It's hard to get government to agree, because it's like the law of the oceans, which of course has to be international. And this is an issue which has to be addressed in the context of space. But that's a big challenge. The lawyers will benefit from it, but I think no one else.
Absolutely, yes. And you mentioned the issue of constellations and their effects on astronomy. And that's something that will actually come up on the second day of the conference quite heavily. So anybody in the audience who's watching that may be interested in that side of things, please do check out the program for the second day. And I'm sure there'll be plenty of opportunities to look into that further. And I think this is a good opportunity as well. I know something that you're very passionate about is the light pollution side of things. And you've mentioned that there's activity in the House of Lords with regards to that. I wondered if you could expand on that for our audience.
Yes, if I might, it's slightly off the main theme of this conference, of course. But light pollution is something which concerns astronomers. But one point I'd like to make is that it shouldn't just concern astronomers for two reasons. First, light pollution is a waste of energy. It's also, as we've learned, something which affects the natural world, because if there's no proper darkness, it affects the way various species evolve. But I think more important than that, we should realize that the dark night sky is part of the human environment. It's been something which has been viewed by all human beings in all parts of the world throughout history. It's a long common part of our environment. And it's rather sad that many young people today grow up never seeing a dark sky. And if they live in towns, they never see a dark sky, just they never see a bird's nest. And that's rather sad in both cases. And that's why it's important to try and reduce light pollution. And of course, there are areas of the country, the Brecon Beacons and Northumbria, etc., where they are trying to have areas where you try especially hard to preserve dark skies. But the point I'd like to make is that it's broader than an astronomical issue. And to give an analogy, I'm not an ornithologist, but I would certainly miss it if there were no songbirds in my garden. And similarly, you don't need to be an amateur astronomer to feel that you're missing something if you never see a dark night sky. So that's why I think it's good if we do try and ensure that we minimize the pollution from floodlights, etc., and street lights that are on unnecessarily.
Absolutely. I think, yes, as someone that's grown up in the city, for the first time I went to the observatory in La Palma, that was quite a revelation, really,
yes.
to see.
And the reason I wanted to mention that is that there's a bill going through Parliament, the Environment Bill, and there have been amendments made, particularly on the issue of light pollution as part of this rather long and elaborate Environment Bill. So this is a time when legislators have at least been made aware that it's an issue that many people care about.
Yes. Yeah. So I guess moving back to the sort of main theme of our discussion, what would you say is the role of the scientific community in preserving the space operating environment?
Well, I mean, obviously, we should use our personal contacts with people in these companies, like SpaceX, etc., to ensure that they're mindful of these concerns. And I think, as in any issue which needs government action or political action, then we should bang on and promote the concern, because we can talk among ourselves, but it's more important that we use public figures and charismatic figures to get press attention and to get public attention, because politicians don't listen very much to expert advisors except in emergencies like COVID-19. I know lots of people who've been advisors in government departments, and since politicians have lots of urgent things to worry about, it's hard to get their attention to long-term issues. But they do care about what's in the inbox and what's in the press. And so I think if one can do what one can to ensure that there is press coverage of these issues about the risk to space, then that's important. And of course, it is a serious issue because it's almost irreversible. Once you've got too much debris in low Earth orbit, it's true that there are clever techniques to put a piece of netting around the big bits and drag them down, but that can't be done with the small bits, which can still be dangerous. And so I think we've just got to make sure that this is something which all those who are involved and the administrators and the military are aware of the issue. And that's why this conference is a good start. And I hope to get a bit of publicity for it in the press.
Thank you very much. We hope so too. So along similar lines, sorry. I guess you talk about building those connections and making sure that we're getting that publicity. How can the different sectors work together? So industry, government, academia all have big parts to play, of course, in tackling this issue. How can they work together better to tackle this problem and keep space safe and sustainable?
Well, I think it's important that when we consider any satellite launch that we're involved in, then obviously one should consider what's going to happen in the long run. Is the spacecraft in low Earth orbit that it will be degrade safely, or is it in a high orbit, in which case we needn't worry so much about it. So I think we've got to be concerned if we are involved in satellite launches. And I think in addition to the very large constellations we've mentioned, there are small satellites which aren't quite so large in number, which are important. I mean, for instance, I know quite well the company Planet Lab, run by Will Marshall, a Brit who used to be at Leicester. What they do is they launch satellites about the size of a fridge. They launched about 70 of them in one Indian rocket, and these are monitoring the Earth. They are scanning the Earth, and their mantra is to observe every tree in the world every day. And they can more or less do this, and this is valuable data. And so I mention this because these are satellites which are slightly different from the constellations used for internet coverage, but also it's important that they are concerned about the fate of these because they're rather short-lived spacecraft. So that's one point. But I think we should consider the international dimension, and particularly the threat of space weaponry is something which is a long-term concern, and that can only be legislated by some international agreement. So I think bodies like the G7, it'd be nice to see that that's at least on the agenda. And I think it's not hopeless to do that because from what I know about these big international meetings, it's often very hard for them to agree on the most important issues to them. So it's often nice if they have something which they can agree on, even though it may be in a sense minor. And so I think the possibility, if there is one, to put on the agenda for big international meetings as something connected with keeping space safe, as it were, is a good idea and worthwhile.
Yes, definitely. And I think that's a good opportunity to move on to the G7 summit. Obviously, it took place in Cornwall earlier this summer. So that at that time, the delegates did actually pledge to take action to tackle the growing hazards of orbital debris and congestion in space. Do you think that will be a key driver for a wider adoption of existing mitigation guidelines? That's obviously a problem that's existed for quite a number of years. And in what way do you think this will help in boosting efforts from a policy perspective?
Well, that's the most recent example of what I was saying, that at every meeting like that, it's important to try and get this issue on the agenda because, as the previous G7 showed, that's slightly easier to get agreement on that than on the other things which they didn't get agreement on. And so I think it's important to do it, and also to ensure that one can get through to those who are concerned with the military use of space, which of course is a more closed world for most of us.
Absolutely, and I had a question relating to UKRI, who support GNOSIS in the form of we're a 21st century challenge network. So looking to bridge that gap between academia and industry and bring different researchers together to tackle this issue. So with that in mind, if UKRI is to be involved in this area, how can they empower the scientific community to get more involved and to tackle this issue?
Well, I think they are facilitators because it's bodies like STFC, which are more hands-on, and they should let STFC make the relevant decisions, and also perhaps Innovate UK, which has some links with industry. But I think it can best be done perhaps by individual contact within the UK, because there are many of us who know some people who work for the space companies, and I think that's a way we can have some influence.
So just to bring us to the close now, Martin, you were the co-founder of the Centre for the Study of Existential Risk. And of course, this sort of topic of orbital debris and congestion in space is unlikely to be an existential risk for humanity, but certainly for human society, it could have quite the impact. So I wondered if we could get your perspective on that.
Yes, well, of course, it's not, as you say, an existential risk, because we have lived very happily without space until 50 years ago, and so we could again. But I think we've got to realize how much we do depend on space technology for communications, obviously, for sat-nav and GPS, and for environmental monitoring, and for weather prediction and all the rest. And if low Earth orbit or geostationary orbits became so clogged up with debris that they couldn't be safely used, this would be a detriment to our present lifestyle. So it would be something that we should feel motivated to try and avoid, even if it's not an existential risk.
Excellent. Well, thank you very much for your time, Martin, and it's been great to talk to you. Yeah, it's been great to hear your insights on the topic. So I'll now be handing back to Don, who will be slightly in the future for us, but at the time for the conference, he'll be introducing the program for day one. So
thank you very much, and best of luck with the rest of the conference.
Thanks very much, Martin.
Well, there you have it. Insights from the Astronomer Royal. Thanks to James for the interview. So that brings us to our conference. So you can see we've got some handles here. Please use them when you talk about the conference. Let's generate some publicity for this area. What you'll find is that the program is actually pretty varied. Some of it's exciting, some of it will be controversial. There's some good plenaries, panel discussions I'm particularly looking forward to, and then parallel sessions, of course. I'll be launching the Warwick new Centre for Space Domain Awareness during the network session. I hope to see you there. So I hope you enjoy it, but the most important thing is that this is an interactive, we're a networking group, so please be interactive in this. So just to remind you, if you look at your virtual client in front of you, if you can, please enter some basic details about yourself if you haven't already done it. And then go to the meeting hub during the networking sessions and say hello to people and have a chat. We're hoping to set up a few little rooms where smaller groups of people can go and discuss things, but please go and please speak. Couple of housekeeping points. I think the most important thing here, you can read it, but the most important thing here is don't use the back button on your browser. If you do, you will have to log back in to the host. If you look in the top left, there's a back to timeline button. When a session finishes, or if you just want out of whatever you're in now, click the back to timeline button. Okay, that will save you a lot of grief. If you have questions, submit them to the speakers through the Q&A session, and the session chair will read them. There's a discussion forum for general chit chat amongst attendees, and most important rather, is that there's a red live support button at the top right of your screen. If you're having any problems, just click that, and someone will come and help you if you have a problem. So with that, that's the end of what I've got to say, and I'm now going to hand you on to Stuart, who's going to introduce the speakers for this session and take questions. Over to you, Stuart.
Thank you very much indeed, Don. So Don introduced me as one of the program managers for the GNOSIS network. And if you're wondering what a project manager does in this network, the answer is whatever Don tells me. So anyway, my pleasurable task this afternoon is to introduce the first two speakers in the first session of our conference. So I'll move straight on to that. Our first speaker today is Camilla Colombo, who is currently the Associate Professor at the Politecnico di Milano in Italy. And she has previously had connections in this country with the universities of Strathclyde and Southampton. Her title today is Space Debris and Steps Towards the Sustainability of the Space Environment. So Camilla, if I can invite you to give your presentation, and then I'll rejoin for questions at the end of your talk. Many thanks.
Good afternoon, everybody. It's a great honor for me to participate to this conference. As it was said, I worked for 10 years in the UK, so half of my art is still in the UK. So in this presentation, I will try to give an overview on the space debris problem and comment on steps toward the sustainability of the space environment. So as we are all now aware, space and services from space are now fundamental for our life on Earth, because many of the activities and services that we use, for example, on our mobile phone are coming from satellites. We can think about weather forecast, long-term climate monitoring, communication, the study of the interaction between the sun and our atmosphere, geolocation, or monitoring in general of the activity of the condition of our planet. They are all services which are guaranteed by satellites. Indeed, if we have a look at the satellites that are currently orbiting around the Earth, there are many of them. And if we try to map all these satellites and what they do in a map in a planisphere, we would get something like this. So we did the exercise of trying to map all the services, divided in very easy to understand categories like vegetation studies or ice studies or radar tracking or geolocation, and to map them with a simple color mapping the location on the Earth which are using these services provided by satellites. And then if we try now in 2021 to get rid of those services, this would be what would happen to the planisphere, basically to our knowledge of the Earth. So little by little we would get rid of all these services and this knowledge, and we would live, let's say, in a planet but with less knowledge about it. This is all guaranteed by the many satellites that have been launched in orbit since the beginning of space activities. 6,000 have been the number of launches since the beginning of space activities, and these launches put in place around 12,000 satellites, of which in August 2021 only 7,000 are still in orbit, but only 4,600 are the satellites still functioning. Yes, because together with the operating satellite, there are a huge amount of space debris. And in particular, if we want to continue a bit with the numbers, 29,000 is the number of space debris which are currently monitored by the surveillance network. And however, these are not the only space debris. In fact, if we want to look at the space debris of a smaller size, we need then to use statistical models. And if we go down to the debris, for example, of the size between 1 centimeter and 10 centimeter, which is still damaging emission in case of a collision, we are talking about 1 million of objects. And if we go down to even the smaller debris particle, we are talking about 330 millions of objects. And to give even more the feeling of this situation, if we would imagine of launching the Apollo mission in 2019, so 50 years later from the actual mission, This would be the situation that the satellite would have to pass before entering into the interplanetary mission to the moon, in the interplanetary trajectory to the moon. And looking back at our planet, we would see the ring of artificial particles that we have created during the space activities. And if we think about the space debris problem and the problem of space sustainability, we can see that it has many similarities with other environmental issues. For example, just to give an example, the problem of plastic in the ocean. And this is also demonstrated if we compare the Earth system trend, the environmental stressors characterizing, for example, the growth of carbon dioxide or tropical forest loss or ocean acidification. And if we compare this with the proxy of the space debris problem, that, for example, could be the number of objects in space, we would see that also in the case of the space debris problem, we have the typical exponential behavior proper of this kind of environmental issues. Now, going a bit more into detail about the space debris problem, we can have a look actually at the evolution of the number of objects in space from the beginning of the space age till now, by looking, for example, at the European Space Agency graph that shows the number of artificial objects in orbit, divided in between the contribution of rocket bodies and payload, and divided in between let's say active satellite or the main body and mission related object or fragmentation objects. And what we can note is that there are two very large increase in the number of the debris count, which were the two well-known very important fragmentation, for example, in 2007, the anti-satellite test, and in 2009, between the Iridium satellite and the Cosmos satellite. These two examples show us in this graph how each fragmentation contributes to the global population of space debris. And in fact, if we plot all the fragmentation happened in orbit between the year 2000 and 2018, we can see in this graph the orbital position of this fragmentation, and the size of them is represented by the number of fragments released in orbit. And each one of these fragmentation, even small fragments, can have a detrimental effect on current and future space mission. One example is for example, represented by this picture of Sentinel-1 solar array before and after the collision with a sub-millimeter size particle in 2016. Every time a fragmentation takes place, the evolution of fragments has got a particular behavior. In here, we look at the behavior in low Earth orbit. We can see that at the beginning, fragments are focused in the point of fragmentation of collision. But then, due to the effect of orbit perturbation, they evolve in a toroid around the Earth, and then, due to the effect of the oblateness of the Earth, they start creating a band around the Earth. So a single fragmentation in a single orbit location will affect on the long term many other orbital regions. As example, we can see, for example, a rocket body explosion in a sun-synchronous orbit, in circular orbit, so a particular populated region, and we can characterize the debris evolution in different kinds of plot, very representative plot in the debris field. This one, for example, is the Gabbard diagram that shows the evolution of the location of fragments in terms of semi-major axis and eccentricity of the orbit. after the fragmentation, right after the fragmentation, with this very characteristic V-shaped diagram, and then after, in this case, 3,000 days after the fragmentation, where you can see that the left graph of the left part of the graph disappeared because fragment decayed thanks to aerodynamic drag. And if we look at the evolution of this fragmentation in time, what we could see is the peak where the fragmentation happened, and different species of debris object which are characterized by a different area to mass ratio, a different cross area and a different mass, and therefore by a different dynamical behavior, a different orbit evolution. And we can characterize how this single cloud will evolve in time. So we add here another line which represents time evolution, and so that we study how this cloud evolves in time, how the peak will hopefully decrease thanks to the effect of aerodynamic drag, and how the wave of this cloud will enlarge due to the effect of orbit perturbation. So it's really like studying the evolution of a wave over time. And in particular, we can see, for example, what is the dilution time. So the time that it takes for this single fragmentation cloud, for the density of this cloud to halve its value. And as we can see for this graph, the time it takes for this fragmentation to dissolve depends on the altitude where the fragmentation took place and the area to mass ratio of the object. In particular, the higher is the altitude of the breakup, of course, the longer it will take for the cloud to dilute, and also the dilution time increases for decreasing values of area to mass ratio, because the effect of orbit perturbation is lower, the effect of drag is lower. Looking at this problem, what are the challenges associated to the space debris problem? I will try in the rest of my presentation to give you some spot on what are the main questions, the main challenges, and what are the current steps in this direction. Of course, my presentation will not be able to cover over all the challenges, but just to give you a hint and a taste of them. So we said that even small fragments are detrimental to space mission because actually they can collide at very high relative velocity with the operational satellite, and therefore they can damage emissions. So first of all, how to model such a large number of objects. For this, there are several debris evolutionary models developed by institutions, space agencies, and usually they are cross-validated within, for example, the Interagency Debris Coordination Committee or within other collaboration efforts. There are two families of long-term evolution models, statistical models and deterministic model. It's important to highlight that they do not predict the future. No one can really predict the future, but they study possible evolution under different hypotheses, because of course we need to make hypotheses, in particular on the future launches, the future trend in post-mission disposal and the adherence to them, the future collision and fragmentation, and also how to model collision and fragmentation in space, and the dynamical model, so the evolution of solar activity and the density of the atmosphere, that is very difficult to model and to predict. Therefore, all the results are always given thanks to statistical distribution. And at the right of the slide, there is an example of the characterization of the density of space debris through a continuum approach that characterizes the density in orbit as it changes in space and in times. But then if we are able to model space debris, their position and their evolution, the next step is how to monitor and reconstruct possible fragmentation in orbit. And in particular, when there is a fragmentation, we can observe fragments thanks to telescope on ground or orbiting. All these fragments are cataloged within the catalog, but many of them remain unidentified. So the one challenge is how to connect possible observed fragments to the parent satellite. And this process requires a procedure that is able, first of all, to characterize all the fragments, then to filter among all the possible fragments in the catalog, the one that for geometrical reason they cannot be associated to the same fragmentation event, and then by using orbit propagation and the characterization of the orbital elements in time, what we can do is to identify the epoch of the fragmentation and identify the most probable possible parent object, and therefore at that point we can characterize the fragmentation in space. Once the fragmentation is characterized, we still have another challenge, that is to avoid this fragment in space. So how to design collision avoidance maneuvers. This is a very challenging task because it requires optimizing the maneuver in order to avoid the collision, but the collision event will always be affected by some uncertainties. Therefore, the maneuver can, for example, be designed in order not to avoid for sure the collision avoidance, the collision, but to minimize the probability of such collision happening. What are then the other challenges associated to the space debris problem? If we can deal in the way I said with the small fragments, how can instead we promote a sustainable use of space? For example, how to make economically viable end-of-life disposal of satellite. This is the example of an ESA mission, the integral mission that was in high elliptical orbit. As you can see, the orbit is affected by orbit perturbation and therefore it evolves in time, in this case thanks to the moon effect. And in the case of this mission was exactly the perturbation of the moon that was exploited in order to design a disposal maneuver, to design a maneuver that actually was implemented in 2015 that allowed the satellite to move on a different orbit, and then thanks to the effect of natural forces, this orbit will evolve over a very long time into a re-entry orbit. So this satellite will re-enter in 2029. And this is an example on how artificial maneuver and the knowledge of the natural dynamics can be used in order to minimize the propellant consumption for end-of-life disposal and therefore minimize the cost for being sustainable. Then other ways to promote a sustainable use of space is to perform accurate re-entry prediction, because re-entry prediction are associated to very large uncertainties due to the factor that I mentioned before. It's very challenging to perform re-entry prediction due to those uncertainties. Therefore, also re-entry prediction are done through, let's say, statistical approaches, which consider the effect of uncertainties at the boundaries of the interface with the atmosphere, usually 120 kilometers, and propagates those uncertainties down to the ground to calculate the casualty risk on ground. Other ways to promote sustainable use of space are instead active ways of removing debris, because so far we have spoken about passive debris removal. So there have been many technologies and many proposals for active debris removal. In here I've reported some of them. And what are some of the challenges associated to active debris removal? First of all, the design of a close approach trajectory to the space debris. And in this example, you see a characteristic spiraling trajectory that approaches the target in a spiral way in order not to collide with the target while approaching. And other challenges are associated instead with the fact that the target can be rotating also at a fast speed, and therefore there are different solutions for detumble the satellite. One of them, that is just an example, can be done by using the exhaust gases of the engine to reduce the rotational speed of the object. And if we have seen some of the ideas and challenges for, let's say, tackling the problem of debris mitigation, we have to consider that we are now in the new space area. There are new frontiers in the space activities. So how to harmonize the boom of space activities, the fact that due to the privatization of space, we are seeing a lot of more satellites being launched, and the future sustainability of space. And associated to this, the next question is how to measure the capacity of the space environment, because we can see the space environment as our new frontier of the ecosystem. As we have seen before, there are many analogies between other environmental problems and the space debris problem. So, first of all, at the mission level, how can we design new missions? There have been many initiatives to perform a mission life cycle indicator of the mission. So, to design the mission considering all the phases of the mission in a circular way, and in an attempt of including also in this life cycle indicator the impact of space debris on the life cycle assessment. The impact of space debris, including the fact that we are using an orbit, which is a resource, like a natural resource. There is a risk related to collisions and explosion in space, a risk related to casualty risk on ground, and also including the potential of pollution of the satellite demising during re-entry. Also, how to assess the capacity of the space environment. One current project is looking at the creation of an open software platform for the evaluation of the impact of the space debris mission onto the space environment, considering high-level information of the mission, such as the mass of the satellite, the cross area, the orbit, the risk that this mission has associated to fragmentation in space, and the effect of this fragmentation onto the other satellite. And also how to assess the global overall capacity of the space environment. And the idea is to arrive with an output that is a single score that is suitable for comparison and for integration into a life cycle assessment procedure. So all the techniques that I showed before are then used in this exercise in order, first of all, to characterize each one of the possible fragmentation in space in terms of the distribution in orbital elements at the fragmentation, and then later days after the fragmentation, and then given the result of this fragment evolution to determine a so-called space debris index. This formulation is one of the many formulations that have been proposed in the literature within the international community, but I use it only just to give you an example of how a space debris index contains. So it contains ingredients which are referring to the probability of a collision happening in space or an explosion happening in space, the term P, and then the effect that such a collision or explosion will have on all the other orbiting satellite, active satellite. This index is then integrated over the overall mission of the satellite and contains all the characteristics of the mission. So the end-of-life disposal, the reliability of the end-of-life disposal, the capabilities of performing collision avoidance maneuver during the mission, and so on. So in this presentation, we touched many of the challenges associated to the space debris problem, and also what are the current state of the art of solutions, of how to find a solution and how to assess this sustainability problem, space sustainability problem. And for sure, one thing is already certain, that space debris, as all the other environmental problems, is a global issue. So the solution to the problem of space sustainability requires international cooperation. This is done for sure within the Interagency Debris Coordination Committee, but with all the effort by operator, by service provider, by space agencies, by institutions, by companies, in order to actually be responsible and be collaborative. And if we can list some of the open challenges for the future, for a more sustainable space, these are some examples that, of course, are not the only one. So we are seeing in these years and in the future the development of space traffic management, so techniques and procedures in order to manage space traffic, like we already know how to manage now air traffic. Then the large number of objects will require autonomy of operation, and in general the development and improvement of space debris mitigation, both passive debris mitigation and active debris mitigation. This will require also more in-orbit tests, because many of the models need to be validated, and also in general, we will need and require a responsible behavior by all the companies and institutions in the public and in the private sector. With this, I conclude my talk. I would like to thank my research group in Milan, because many of the examples that I show you here have been done by them. And I would like to acknowledge the funding that made this research possible. With this, I stop, and I'm available to answer any question.
Many thanks indeed, Camilla, for a super introductory presentation for the conference. Thank you very much indeed. I wonder if I could start by echoing one of the questions that's come in from my joint program manager, Dinsley. Touches on the issue of the difference between some of the figures that you quoted in your presentation and some of the numbers that are coming out of NASA at the moment, partly in terms of the number of active satellites, but also the figure that you quoted for the total number of objects in the size range 1 to 10 centimeters, which you had as about 1 million objects. I believe that NASA's estimate of that number is on the order of 500,000, which is a difference of a factor of 2. Would you care to comment on the differences between the models that are generating these differences in numbers?
Yeah, thank you for your question. Actually, just to be sure, I checked all the numbers before today, and as I wrote, I used as a reference the European Space Agency report of space debris. So I think that these numbers are, let's say, in agreement up to, of course, the catalog number of objects, while when we start speaking about the untrackable object, then, as I said, they are given by statistical models. And the reason why at the IADC we always work with the cross checks is that this statistical model, they have different modeling hypotheses behind. The main differences are due to the breakup model, because a different breakup model will give a different number of objects at any of the collision, and there are different models being developed, for example, at NASA, at Aerospace Corporation, at ESA, and they are based on physical information, physical equation, but also by empirical models and experimental activities, and they give different results due to the fact that we don't have many experimental activities on this. And also due to modeling of, for example, the atmosphere, so the knowledge of the atmosphere. So the statistical models will give different numbers. This is why we always work with the mean, but then also the standard deviation of them. And therefore, this is why this number cannot be taken as, let's say, a future evolution, but they have to be taken as estimates.
Yes. Obviously, one of the things that we would like to be able to do is to move from a regime where actually just modeling the population that we think is in orbit around the Earth and actually get reliable measurements of the actual population. Do you have a preferred route that we might take to actually get those sorts of accurate measurements to actually understand which of our models is giving the best predictions?
Yeah, I think that in this direction, it's very important to link the communities of modelers and, for example, observer, because validation from observation, either on ground or in situ, are very important to cross-validate models. Because then these models are used to define policies, to define mitigation rules. So I think this can be tackled with many more exercises of cross-validation with actual experiment, both from, as I said, on ground, but also on orbit validation. So, for example, on orbit validation of small particles, also the reconstruction of a fragmentation requires a lot of validation. So I think that, yeah, the solution is only more and more validations.
Yes, I think that's entirely correct. We've had a couple of questions relating to the sort of capacity that might exist in low Earth orbit. Are we able to sort of estimate the sort of carrying capacity, if you like, of low Earth orbit? And do you have a sense of what proportion of that carrying capacity the current debris population might represent?
Yes, unfortunately, I couldn't go into much detail about that, but there are several studies about the calculation of the carrying capacity in space, and this carrying capacity is, let's say, calculated by summing up all the debris index associated to all this mission. I will not give any number because I think that in this area we are still in the area of really hot discussion, international discussion about that, because I will just answer with an analogy. When for climate change, it was set the degrees that we need to decrease the temperature of in order to, let's say, avoid the problem of climate change. This was the result of a very long international collaboration and discussion. So at the moment, these discussions are actually going on, in the sense that, for example, ESA and other space agencies, they have their calculation of the capacity, but we are not yet there at really discussing, first of all, what is an acceptable threshold of it, and also even how to measure it, which in other fields at least is already reached a consensus.
Yes, I agree. I think until we reach a consensus on which of the population models is accurate, it's hard to actually estimate how close we are to the Kessler threshold already, and how much more debris we can stand, if you like. We've had a couple of questions, one from Kit Lee and another from Fiona Thompson relating to debris removal. Do you think that those proposed taking stuff out of orbit do have a commercial business case and a viable future?
Personally, I think so. There have been many, let's say, studies and proposals for active debris removal. I think that some of them will have a better business case than other, and probably, in my opinion, are the one associated to not really the active debris removal of large rocket bodies, because at the moment there is not really a revenue to remove them, even if there is a lot of interest from the space debris problem point of view. While I think that in terms of, let's say, business case, probably a service for active debris removal of a large constellation satellite is going to be more economically viable on the short term, because it's not only a sustainability debris problem, but is also an economical problem of removing the damaged satellite in order not to damage the service and the mission. And hopefully in the future also the active debris removal of single object will become viable, but I think it will happen only when guidelines of debris removal will become actually regulation and binding.
Yeah. One of the things that particularly intrigued me about your presentation was your talk with the part where you talked about the evolution of debris. And in particular, I'm interested in the evolution of the very small debris, because I attended at the Royal Astronomical Society here in the UK a few years ago, where it was suggested that very small sort of millimeter-sized debris has an area to mass ratio that means that its lifetime is potentially measured in weeks to months rather than the years to days of objects. I mean, do you share that view? And is the estimate of the small debris that you mentioned, taking that sort of likely decay of the small debris into account?
You are referring to the selection of object for active debris removal?
No, not particularly. It's sort of the natural lifetimes of the very small objects. I've heard it suggested that they are very short because they respond to solar radiation pressure to a much greater extent than larger objects. And
yeah. Okay, thank you. It's true that in low Earth orbit, so when aerodynamic drag has got some importance, high area to mass object, they have a shorter lifetime than larger debris. So small fragments or even satellite equipped with the solar sail, they deorbit much faster. But this is true only up to 600 kilometers altitude, because above that, then solar radiation pressure also becomes important and is also function of the area to mass. So small fragments above 600 kilometer altitude will evolve in a very, let's say, strange or unpredictable way, and therefore their orbit will change a lot. One example is small debris fragments in a geostationary orbit that do not stay in geostationary orbit, but evolve in elliptical orbit and then come back to the geostationary ring. So I think that the study of their dynamics, it's very important, because maybe you can find the area where you can collect them, or at least you can avoid them.
Sure. Yeah, I mean, the thought that occurred that statement at the Royal Astronomical Society a few years ago was, well, do we have to worry about the very small debris, in that if its lifetime is very short, it'll re-enter and we don't have to be concerned? Or, do we have to take into account, very large populations of very small objects of the sort that you're describing? Yeah. And, if there really are that many objects in Earth orbit at the moment, does that mean that, because their lifetimes are short, they're actually being created at a very high rate by collisions either with other pieces of debris or possibly as a result of collisions with natural micrometeorites?
Yeah, no, I think we do need to worry about them. Actually, Darren has done a very nice work on characterizing the possible causes of them, because it's not only collision, it can be explosion, it can be deteriorating of surfaces, or it can be malfunctioning of batteries, systems of satellites. So it's also important to design satellites in a way that they are going to be releasing the least amount of these small objects, which are not completely damaging the mission, but they are, for example, damaging operating payload, and anyway they are polluting.
Yes, I mean, clearly there's a variety of mechanisms by which we can end up with debris. Collisions are one of them, and as you've mentioned, sort of malfunctions of satellite batteries and propulsion systems can lead to the of satellites as well, and those different mechanisms, I guess, are going to generate different populations of debris fragments, which just complicates the matter still further, I guess. We've had an interesting question from Anthony Rushton, which is, how might we better incentivize industry to safely manage the LEO capacity?
I think that the only solution that I see is really to work at the international level in order to bring these mitigation guidelines, which are defined and agreed internationally, into national laws for launching satellite for the operator, and also in the licensing request. So the ideal situation is if in the future, before you launch a mission, you can have your space debris index calculated, therefore the share of the capacity that you as a mission will use in the future, and therefore depending on that share you will maybe pay more or less. In that way, you will be kind of economically forced to be more clean and more sustainable. And I think that at the moment, many companies are, let's say, anyway, working in a responsible way, but I think it's more, let's say, driven by the image that they have in the community.
Yes, I mean, Lord Rees made reference to, sort of interacting with makers, and Catherine Courtney's question is about how we get this on the agenda of global leaders. I guess to some extent there was some recognition of this subject at the recent conference in the UK, but are specific things that you think either space agencies like ESA or individuals should be doing to try and further raise awareness of this issue?
So from one side, for sure, the collaborative effort in between space agencies is fundamental, not only in the capacity, but also in the future space traffic management. So there should be the effort by all the agencies to actually collaborate on this, because it cannot be done by one single agency. And on the other side, and this could be done at the, for example, at the Interagency Debris Coordination Committee, or all the communities where you gather in all the different players from different nations. One other maybe step could be also to raise awareness. So in order to, as everything, in order to make policies take decision faster in any field, you need to raise awareness. So I think that also it's important by everybody working in the space community to help and to contribute into raising awareness of the space debris problem, and also the fact that actually our life are dependent from space. So no one can really think to be excluded by this unless you decide not to use any service from space.
Yes. If I could ask you one final question before we close. It was observed by John Owen that we have an existing regime for the coordination of frequencies for satellites. Do you feel that inevitably in the end we will need, as part of a sort of space traffic management or space traffic control capability, the need to have an international mechanism for coordinating the orbits of satellites as well?
Yeah, on this, there have been some studies and discussion where actually the frequency coordination in some cases, like for example in geostationary orbit, kind of naturally brought to the fact that satellites then are in certain given slot, because if you could go to the same slot, but if the frequency is already allocated, there is no point for you to go to that slot. So maybe what could happen is that a procedure similar to the frequency allocation could also be organized and planned for, let's say, orbit slot, or even the two things could actually be linked together. And for example, I think that this is also in some way happening for large constellation, because now due to the boom of large constellation, they cannot really go to the same orbit. So at the moment, the way is more the first come first serve basis, which is actually the same rule for the frequency allocation. I guess that for the future, as we have seen, for example, for air traffic management, a more ruled procedure will have to be put in place, given values to orbit or to frequencies, and defining a way in which these orbits are allocated.
Yes, and I hope we'll be able to get some international agreement on a process to achieve that. But can I indeed for both your presentation and your very coherent answers to the questions. I hope we've managed to touch on most of the issues that were raised in the questions that arose, and we will address the other questions offline afterwards, if that's okay. But what I'd like to do now is to move on to the second presentation that we have in this first session of the conference, which is going to be given by a very good friend of mine, Darren McKnight, who has been asking challenging and provocative questions in this area for many years, and has recently joined the company LeoLabs, which is, if you haven't come across it, a company that's endeavoring to build a network of radars to track stuff in low Earth orbit. Darren's title for us this afternoon is The Dangers of Debris and Rocket Bodies. So Darren, if you're ready, perhaps I can hand the floor to you, and I'll join you again for the questions a little later. Many thanks.
Sure. Thank you very much. And Camilla, thank you for that great introduction. I really appreciate the opportunity to speak with you all today. And one of the things that Camilla talked about was the concept of models. And so when we were talking about modeling of debris, it struck me one of the great papers, if you haven't read it before, by George Box on science and statistics. All models are wrong and some are useful. And so I think that really holds true a lot in space debris. And one of the reasons why I did come to work at LeoLabs was because really it gave me an opportunity to leverage our global network of S-band radars to actually do measurements and look at doing experiments empirically what's going on in Earth orbit. So what I'm going to focus on a little bit here today is focusing down on first some things that are pretty clear. As Stuart said, I sometimes say things that are a little provocative. Collisions in space are bad is not one of those provocative comments. But I want to tell you that really that's kind of the root of everything that we're worried about. Obviously, explosions and deterioration of spacecraft are important, but collisions are important because of the fact that they're going to create lots of debris. And so the main message I want to get across today, if I can get one main message across, is that we need a balance between space traffic management and space debris management. The charts I'm going to give today are really sort of the appetizer for the full course that we'll be giving next week. I'm giving a keynote at the Stardust workshop next week. So we had a little shorter period of time, and I want to make sure we had a lot of time for question and answers here. So if you see some things you think are interesting and you wish you could see have the full course meal, that full course meal will be next Friday. But this hopefully will be a tantalizing appetizer. So space traffic management is really about avoiding collisions that involve an operational satellite. So if you have an operational satellite, I don't want to get hit. And what can you get hit by? Well, and on this chart here, one is a trackable objects. There's things that are in the catalog as they currently exist, in the catalog that gets maintained by the 18th Space Control Squadron and folks at ESOC and also LeoLabs. We're all basically saying about 17,000 objects in low Earth orbit, greater in size than 10 centimeters. And so we want to avoid those. It's very important to avoid them. But as this graphic shows, by avoiding the trackable objects, you've really avoided about 2 to 5% of the mission terminating risk. It's really this lethal non-trackable debris that really is a concern, because what you cannot see can kill you. I also want to note that the lethal non-trackable debris may very well go down to 5 millimeters, depending upon the sensitivity of the systems and subsystems on your spacecraft, how you're oriented and what material it's made out of. But roughly 1 to 10 centimeters is definitely, that stuff is bad. That stuff is going to kill you if it hits you. And it really poses about 95 to 98% of the mission terminating risk in low Earth orbit. And as a matter of fact, I'll even tell you, I had some good discussions with Don Kessler lately. He's tried to be retired, but we don't let him retire because we call him all the time and chat with him. And one of the things that he wanted to make sure people understood was the Kessler syndrome talks about this cascading effect of breakup events. However, implied in that syndrome is actually what we call, Don and I call it, the mini Kessler syndrome. And that is the cascading of mission terminating effects, maybe not breaking up satellites, but causing satellites to fail prematurely. That's actually going to be a precursor to the Kessler syndrome that people want to talk about all the time, the catastrophic collisions. So we're paying real close attention, monitoring and characterizing and informing the space community about some of these other lesser impressive events, but they are going to be the indicator, the precursor for the other events to follow after that with the catastrophic collisions. So I said we need to balance space traffic management and space debris management. You may say, I never heard of space debris management, and that's because we made up the word. Made up the word because a lot of people talk about debris mitigation, don't litter, debris remediation, pick up your trash. Those two things seem to be talked about as nice to haves. And all I'm going to tell you today, you should walk away with space traffic management and space debris management need to have a balanced amount of emphasis. Let's say, for example, you're driving down the M25 and you know that you had a great fleet of trucks that are sharing each other's location and explaining about who's going to drop off some material at a certain place, a well-oiled machine, kind of like a constellation of cars on the roadway. But if the M25 has potholes and the bridges are out, you're not going anywhere. Same thing holds true here. You could have great space traffic management, very, very important. But you also need to have space debris management, that is mitigating debris and remediating debris. Because when those objects collide, big, massive objects collide, they end up increasing the collision hazard and adds to the burden of trying to do space traffic management. And a lot of the space traffic management is really collision avoidance burden. It puts more of a burden. Matter of fact, one of the things I've been talking about lately, people say, well, constellations, they're bad. And I said, constellations, are they the problem or are they the victim? My assertion is constellations are actually the victim, not the problem. The way that constellations have robust, responsive collision avoidance capabilities within their own constellations, do a great job of station keeping within those constellations, and then avoiding things outside there, much more responsible than large dead objects that have no capability to maneuver. The bad news is many of these large dead objects end up being put into clusters. So we talked about the term clusters and clusters of dead things versus constellations of live things. So let's take a look at how that might look across low Earth orbit. So this is a chart that shows as a function of altitude in low Earth orbit at the 2,000 kilometers, the percentage of mass by types of objects at each orbit. This chart is one that if Stuart were to pour me a nice glass of Pinot Noir, we could sit back, have a little sip, lean, and look at this, and you'll probably see many, many things going on here. But one thing you should see is whatever is the light blue, there's a whole lot of them. Well, that's rocket bodies. So when you think about the percentage of mass in individual orbits, in 10-kilometer bins, it's the rocket bodies that actually have the most mass. So why is that relevant? Well, what I like to say is the current collision risk comes from the number of objects. The future collision risk comes from the mass, because two objects colliding, say two 1,400 kilogram rocket bodies colliding, this can be much worse than Fing Young, much worse than Iridium Cosmos. A lot more mass involved and still very, very high velocities. So this just sort of gives you a mapping of where is there a lot of large, massive derelicts. Notice non-operational payloads are not inconsequential either, but historically the dead rocket bodies have a mass that's greater than the dead payloads, believe it or not. What you'll also see here is a couple of orbits. You see here around 550. You see where Starlink has populated that orbit. So obviously there the mass is a greater percentage of operational payloads. And so many people will say, Starlink, what a bad thing. Look at all those satellites they're putting in. Look at all that they're putting up there. Well, in reality, if you look at the entire mass of the Starlink constellation of robust, responsive, collision-avoiding satellites, small, 240 odd kilograms, agile, be able to avoid each other, the total mass is actually equal to the same mass of 290 abandoned SL8 rocket bodies that have been abandoned between 600 kilometers and about 1,400 kilometers over the last 40, 50 years. And so the mass is equal, except the SL8 rocket bodies have no ability to avoid. They have no intent to avoid, and they're at high altitudes that are going to linger for a long, long time. So again, just start to hint a little bit at the balance between space debris management and space traffic management. So this chart is what we call the heartbeat of low Earth orbit. So this is what's called the LEO collision risk continuum. And if you want to see lots of charts with blue and orange on here, and any of you who follow American football, it looks like the Broncos have done this chart with the colors here. But what this is a chart that looks at the risk from 1.4 million conjunctions that LeoLabs monitored over the last calendar year. And so the blue dots are op versus all. So basically that's space traffic management. Operational payloads avoiding everything, other operational payloads and dead things. So the blue dots are like space traffic management. The orange dots are debris on debris, where debris are both fragments from explosions, collisions, and massive derelicts, abandoned rocket bodies, and non-operational payloads. That is really how debris, that's going to sort of show you what debris remediation can help curtail. So we had 760 conjunctions, 760,000 conjunctions, I'm sorry, that were plotted on this plot that had probability of collision of greater than 1 times 10 to the minus 6. And when we looked at the consequence, we looked at probability, the consequence is the total mass involved. That's why risk on this chart has units of kilograms. So it's sort of the debris generating potential risk from all of these conjunctions. And I said 760,000 conjunctions. I also just told you 1.4 million. Where did those other ones go? Well, there were 670,000 conjunctions within the Starlink constellation. And we didn't look at those. We didn't care about those because this is the great example of us having a mathematical model that we apply to certain situations. We continue to apply it, and actually the results are not appropriate. So within a constellation that's well maintained, it's kind of like the marching band on the football field at halftime. You may have 400 students on the field walking very close to each other at very high speeds, and nobody's colliding. If you win the big game and 400 students storm the field cheering because they beat the crosstown rival, you have lots of collisions. And so unfortunately, the terms that we use for the probability of collision, we sort of assume a stochastic process, where it is in a constellation, it's not. It really is a system that is performing, and if as long as there's reliable miss distances, even if they're high and the distance seems small relative to what would worry us normally, you shouldn't be worried. So this is the 760,000 conjunctions of operational satellites against everything else, and then debris on debris. So what's interesting here, as I mentioned, there are a number of clusters that we've studied in the past, and these clusters are like 750, 850, 975, 1500. But you can kind of see this on this plot. But what we do know for sure is that 65% of the events were debris on debris. So 65% of the events, things that are not being able to be prevented because these are dead objects, amount to 65% of the risk. The greatest debris generating potential, which you can't see on this chart very well, but I'll show you one in a moment where you can see it better, is between 775 and 850 kilometers. What I want to mention real quickly is Camilla and Stuart were talking about the lethal non-trackable population and models. I'll tell you right now, the population, the altitude where the lethal non-trackables appear to peak in number by both Ordom and Master, the NASA and the ESA models for the debris populations are right around 100 to 150 kilometers in altitude. But the two models differ by about a factor of 50 as far as the number of objects at that altitude above 1 centimeter. So indeed, there is a lot of uncertainty, but remember 850, because if you look at this plot, you kind of get a feeling something's going on there. So let's take the next look at this. So I do want to mention that while all of these dots are important, the top 200 are the ones that are really going to drive us and think what these are the things we're really most concerned about. So we're going to drill down the top 200 in a moment and see what's involved in the top 200 conjunctions over the last year. I also want to make sure that we talk about the stuff down below here. This is kind of like the orange haze here, kind of like the fog over the Thames in the morning. That's all the debris interacting with the rocket bodies. It's interesting, but less relevant than these massive objects, because as I mentioned before, the lethal non-trackable debris, what you cannot see can kill you. I care about the big stuff because the big stuff's going to make a lot of the small stuff. As Stuart was talking about, where does this small stuff come from? Well, it comes from events that generate debris maybe at 1,000 kilometers or 800 kilometers from a collision, and the debris gets sent in both directions. Is probably 10 to 25 times more lethal non-trackable debris made from a collision event than what we can actually see in the catalog. So that debris may go to very high altitudes and then wash down over time. So this is a chart where we took the aggregate. So now what we did is all those individual dots by altitude, we added them all up to look at the risk. So what we can see here is only in the region between about 400 and 580 kilometers is the space traffic management really a greater concern than the debris on debris. Well, obviously you know that there's a lot of activity of objects going from the parking orbit for Starlink up to the operational altitudes. So they have had a very big collision avoidance burden with objects that have been deposited 20, 30, 40 years due to the idea of this 25-year rule being a safe, wonderful mitigation policy. And I will tell you that I believe that actually it's irresponsible and adding to the problems for many of these constellations in low Earth orbit, because we're basically saying if you put your trash at 615 kilometers, you're compliant, but then you just slowly work your way down through all of these constellations that are being built in low Earth orbit. Actually, it really defeats the purpose of being safe. But between 400 and 580 kilometers, really, space traffic management actually is, again, more important than the debris remediation. I do want to make sure I highlight this, and you get this. I'll talk about this more in the longer version, the full entree version of this paper. Is that when we look at op versus all, you have to understand that potentially some of these numbers that we give on the probability of collision with an operational satellite, it may be overestimated from what the operator actually saw. Because most of these operational satellites have a high accuracy ephemeris generated by GPS receivers, so they may have a covariance position uncertainty on the order of 5-10 meters, where for us, we might have something between 15 to 30 to 40 meters, depending upon the type of object. So they might actually have registered and considered a probability of collision slightly lower than we would portray, or the 18th Space Control Squadron would portray. So the key point, though, if you look at 850, 975, now this is where things, the debris on debris is peaking. That's a real problem. As I mentioned before, the lethal non-trackable already appear to be peaking in this orbit. The risk of future large collisions are peaking in this orbit. And you notice around 1,400, 1,500 kilometers that the spike up. By the way, this vertical line at 1,500 kilometers was drawn because during this last year's collection by LeoLabs, we fine-tuned the way that we put our new radars online. So for part of the year, we were not looking above 1,500 kilometers. We are all the way up to 2,000 kilometers now. But for part of the year, we didn't. So we didn't show that data because it was incomplete. But there is another little peak there around 1,500 kilometers that we need to be worried about. And as a matter of fact, we were talking earlier about capacity in the previous presentation. And within the longer version, Dr. Hugh Lewis from Southampton University was part of our team on this paper. And we did do what we call a poor man's capacity modeling. And I will say that looking at the approach that we took, that was really Hugh's brainchild, was a very simple approach looking at adds and subtracts based upon collisions and based on atmospheric drag. And what we would say is, and we said in the full paper, is that we believe we are past capacity at 750 kilometers and above. And that's largely not because I'm going to say that collision's going to happen tomorrow, but without remediation of any type, there will be an accumulation of debris above that altitude that would likely result in significant mission terminating or catastrophic collisions in the future. So that's where we stand on that. So I promise you look at the top 200, and I think looking at the top 200 conjunctions is sort of, the hit list of the 760,000 conjunctions. The first thing to note here is that Russian objects accounted for 50%. Some of you may go, wow, that's a lot. In reality, for many of the things we've done in the past, top 50 paper that we put out about a year and a half ago, 13 countries contributed to that. The actual number was closer to 80% Russian objects were involved. In this case, we had 50% Russian, 28% from US, 16% from China, and then smaller as you go down. Yay, China and UK, you're not on the list. Good job. So top 200 riskiest conjunctions dominated by debris on debris, as we said earlier. A very interesting point here is Starlink makes up 10% of the low Earth orbit population, but only 2.5% of the objects in the top 200 conjunctions. So in reality, they are actually, on average, 4 times safer than an average LEO object. Why? Because they're agile, they're nimble, they try to avoid things if they can. But unfortunately, it's tough when you've got thousands of derelict rocket bodies and payloads getting in your way. So what were the kinds of objects involved in these worst case collisions over the last year? Half were massive intact derelicts, right? Again, big, lots of mass, lots of area. So a big, greater hard body radius for you collision avoidance conjunction assessment people out there. 30% fragments, so more with massive derelicts than with fragments, despite the fact there are many, many more fragments. 20% operational payloads. So again, these operational payloads are in harm's way because there's other mess. So what are the types of objects that were most prevalent? I mentioned the SL8 rocket body before. 35 events of the 200 events involved an SL8 rocket body. 2 of the events were SL8 on SL8. Okay, not good. 26% of the events of the 200 involved Fing-Young 1C debris fragments. 21 events involved an SL16 rocket body. For the ones of you who heard me talk before, you're probably surprised I didn't mention the SL16 rocket body yet, but there are 20 of these SL16 rocket bodies in low Earth orbit. 18 of them are within 40 kilometers of each other, between like 820 and 860 kilometers. If two SL16s were to collide, it would double the catalog population in one event. Those are the objects that we need to get rid of. Those are the objects we need to get rid of. And by the way, those 20 SL16 rocket bodies, the mass of those 20 objects would be half the mass of the total Starlink constellation, just 20 objects. So that's that sort of that debris generating potential in these large objects that makes me want to say space traffic management, space debris management should be a balance. The last thing is let's look at individual objects that showed up multiple times, right? Because if you're in the top 200 and you show up multiple times, you're really a bad guy, right? So two of them were old Soviet payloads, and I say Soviet because when they were launched, it was Soviet, old Russian payloads. And these interactions at 549 and 495 were largely with a lot of Starlink satellites. So is that the Starlink's fault for going and avoiding all this, or is it the fault of leaving these massive objects up on orbit? The last two that were showed up 3 times were two SL16 rocket bodies, right around 842, 843 kilometers. So again, trying to really focus in that it's these large Russian derelicts that are the big problem. So that sounds like we can point the fingers at the Russians, right? It's not fair. It's not fair. They talked earlier about what we should do about debris remediation. What I can tell you is the Russian derelicts that are the primary, had the primary debris generating potential, they are high because of interactions with Chinese and US fragments and dead payloads. So as I like to say here, a uniquely ironic collaborative effort of posing great debris generating potential. While it's nice and convenient to say it's the Russians' fault, it really is major spacefaring powers need to be responsible. And to answer a question from the last speaker about what should we do about debris remediation ADR, I believe that the major spacefaring organizations need to get together and say, we need to remediate some of this at its state level and be the leader and catalyze the ADR industry, just like they catalyzed launch vehicle industry. They wasn't all commercial to begin with, just like they catalyzed Earth imaging systems. They weren't all commercial to begin with. But it needs to be the catalyst, one, because it's the right thing to do, because if we don't do it, we're going to have significant problems in the next decade because of these collisions. And number two, show some leadership about space sustainability by doing that. So I want to close on just a little chart about LeoLabs. We talked about the, I think the cool way that the way that we take data. So how do we get this data allowed us to do the heartbeat of low Earth orbit? Well, we have 6 radars around the world, and we currently take more than 400 measurements a day, which is comparable or higher to the 18th Space Patrol Squadron. We provide new state vectors and conjunction data messages within 10 minutes after any object crosses any one of our radars around the world. We really do have a cloud-based computational engine that runs like a 21st century computational engine. So you get your answers within minutes. We don't do anything in batch mode. At LeoLabs, if you talk about batch mode, maybe you're making cookies, but you're not doing space safety. Space safety needs to be a real-time data stream tailored to the operators the way they need it. As a result of our responsiveness of our system, we provide 15,000 state vector updates and 6 million conjunction data messages per day. And by the way, if you say, how does 6 million a day only add up to 1.4 million? The reason is we will track these conjunctions 7 days in advance, and we'll update those as we go through the course heading toward the actual time of closest approach. So you get a real good idea about what's going on with those potential conjunctions, which actually what it does, it provides the operator, our customers, to be able to maybe delay a decision about a maneuver that maybe wouldn't be necessary to do because they have better insight. They know the next time the object is going to cross one of our radars, so it allows them to be more responsive and safer. So what are we going to do in the near future? Well, we're going to start cataloging down to 2 centimeters by the end of this year. We are actually already experimenting with that. I can't share with you the results, but there's a lot of stuff up there. We're going to start to catalog those and put those into our catalog by the end of this year. So we will start to be able to provide collision avoidance, conjunction data messages for objects that previously were not cataloged that are lethal non-trackable. We'll be adding 6 more radars by the end of next year, hopefully more than that, but that's a safe bet. And by the end of 2023, we'll have radars on every continent except for Antarctica, because our job really is to monitor, characterize, and inform people so that we can act responsibly. And that is my talk. I'm looking forward to any questions.
Many, and that was excellent and provocative as usual. Yeah, so I guess going back to your closing point, actually, about the sort of size and magnificence of the LeoLabs catalog, you mentioned the number of measurements that you were making per day, but one of the questions I had in is how many objects does that correspond to in your catalog at the moment, and then how big do you think your catalog will grow to be in maybe 12 months' time when you put the 2-centimeter objects in?
Great question. Right now, I didn't want to make it sound like our catalog is magnificent. It's the same size as the 18 Space Control Squadron for low Earth orbit. So it's around 16,500, 17,000, depending, right? So it's about 16,000, 17,000 objects in our catalog. As far as what it's going to be in the future, we are going to be responsible about how we add these lethal non-trackables in. We aren't going to go, let's try and put all of them in there. And so we can say we have a catalog of 250,000 objects, yay, and have very poor covariance on them, very poor custody on them. So what we're going to do is we're going to work our way down with the higher signal noise ratio on our radars, provide the ones that we can get good custody on so we can give reasonable conjunction data messages out. And so we're going to fill them in responsibly and not just try and make a big pop. We are scaled to operate a catalog at the same pace as we are now, with 24 radars and 250,000 objects in our catalog. So we're scaled to do that. We're not gonna go, ooh, we didn't think we'd see so many objects. We know exactly how many objects we expect to see, and we will put them in a way in which we can maintain custody in a safe way. So the actual number, may go from 17,000 next year to, let's say, 50, 60,000, but it may grow much more than that. Unfortunately, we have to plan for bad things happening, right? If there's a big event, we're going to see a lot more things a lot faster.
Sure. Yeah. I mean, one of the thoughts that occurred to me when you mentioned, that you were going to get down to 2 centimeters is that potentially that starts to allow us to make the measurements that I asked Camilla about to actually differentiate between, say, the NASA fragmentation model and the ESA fragmentation model. Do you think we'll have enough data to do that in the near future?
Yeah, that's a great question, Stuart. And I've recently put together a package called Discovery Families. And Discovery Families are looking at major breakup events that have occurred in the past that have an interesting signature based on inclination or altitude. So it's an inclination that may not be like everything else. And so we are going to try to fold that into our process of getting the small objects to go, hey, how many do we see at 71 degrees? Because 71 degrees is a red flag for an SL-16 rocket body that had popped a few years back, right? Yep. 98.9, we're going to get inundated because we got Fing Young and a couple other things at that 98.9, 98.6. We're going to see majority of objects of the lethal non-trackable, most likely in that inclination. But there are some other inclinations that we're going to look at to try to give some helpful fidelity on that. Yeah, so it'll be difficult within the Fing Young, and I think it's Fing Young and NOAA 16 are the same, very similar inclination. But for some of the other ones, the Rorschach, sodium, potassium, coolant thing, we're going to make a lot of people who've been studying this for a long time pretty happy, because those inclinations will be they'll be red flags for us as we catalog the small stuff, but not for everything.
Absolutely. Another question about catalogs is from Mark Presley, who's sort of asked about the increasing number of catalogs. LeoLabs has one, and the extent to which we can potentially bring these catalogues together. And I think I would add a rider to that question based on the fact that, you know, some catalogues are compiled by governmental facilities and some are obviously, like LeoLabs, a commercial catalogue. How do we do that, you know, improvement of the catalogue by bringing the data together without compromising the commercial business case for SSA?
Yeah, that's a great question. I actually think it really bifurcates into two solutions. I'm not sure how many people are familiar with the term OADR, Open Architecture Data Repository. That's been talked about by the Department of Commerce and some folks in the US about here's how we're going to solve all the problems. Well, I think OADR is a great solution for a better Uber catalog, right? A catalog that says, gets a UN registration, gets Gunter's space page, gets all of John McDowell's great thoughts, you know, and put them into a database about what's the pedigree of this object, how much mass, what kind of radio frequency emanations are there. I think we need to do a better job about that. What are the actual objects? Now, when it comes to the catalog, like you're talking about, to support collision avoidance, that's really going to be driven by how quickly can you update the frequency of seeing the object to provide a new state vector, to reduce the propagation area, to get the covariance smaller so we make responsible decisions. That's going to, I believe, is going to be very difficult to fuse real time, because you've got, by fusing it and saying you can look at many things, you actually get rid of one of the most important qualities, and that is the frequency of update. And because an orbit that propagates for 3 circuits around the Earth is going to be a lot more uncertainty for that conjunction data message than it only goes 1. So that's why we're building out our global network, so that we can provide it what's the most up to date. And by the way, we fuse our data with the 18th all the time for our customers. We show what the 18th has, we show what we have. Just like when a hurricane, goes across the UK, do you just see the UK model, or do you see the UK model, the American model, the French model? I think there's some real benefit to understanding that a tailored data stream to an operator to make the decision is the priority, because that speed is what gets the covariance smaller, which makes the decisions better. So I think there's two kind of solutions that people kind of muddled together in my mind.
Yeah, and I'm very encouraged about your statements about having radars all around the globe in all continents, because it will help to bring down those covariance numbers. I've been invited to go and talk on this subject at Oxford University soon, and one of the points I plan to make is that if you look at the existing governmental networks, they're kind of a sort of strategic Cold War network for fairly obvious reasons, and actually a purpose-designed network, the sort that you're putting in place, would distribute the sensors over a much greater proportion of the planet's surface. So I'm delighted that you're doing that. A question that we've had in from, and I hope I'm going to pronounce this correctly, Nuttapon Nakarach, is relating to CubeSats and the extent to which they represent a potential problem because they, in the majority, don't have propulsion systems. Do you see that as a growing issue in the future?
Absolutely. I think that the debris mitigation guidelines have not done a very good job of keeping pace with space technology. If you look at the 25-year rule and the requirement to show a certain collision risk, there is not a requirement to have collision avoidance capability on a satellite, right? That's just silly. You wouldn't send your kid out in the street driving the car if the steering wheel didn't work. So why are we still doing this? So I think a great answer for this is if you can actively safely control your satellite, go up there and be part of the infrastructure. If you can't, launch from the space station and come on down. You can do a lot from 400 kilometers with something that doesn't have any collision avoidance capability. I just don't understand why somebody hasn't said, so we're going to launch things that can't avoid collisions, but we're going to let it filter down through space station altitude. We're going to filter down through where there's billions of dollars being invested in the space infrastructure, only because we're afraid of making anybody mad. Well, no, I think make people mad. The 25-year rule should be a 1-year rule. And there should not be a satellite that should be able to be launched without an ability to maintain safety. It shouldn't be left to the responsible folks who invest billions of dollars to do all the avoiding of all the dead stuff. That's my opinion. So I think CubeSats are fantastic. They've showed a lot of CubeSats have put electric propulsion and done maneuvers. Tech demos, that was the smallest that they did 2 collision avoidance maneuvers within 2 weeks' time. It's very possible. If you can't afford it, then launch it from the space station. It's great. You get a long time. You get a year of doing stuff, launch a CubeSat from the space station. It's great.
Absolutely on the same page with you on that one. I'm desperately tempted to pick up on your comment just then about the 25-year rule should be a 1-year rule, but I suspect that's another entire presentation. So I better stick to the questions that have been coming in on the chat. So Paul Daniels has made a point that, you know, although perhaps Starlink doesn't constitute quite the most acute problem for space traffic management, it definitely is very much part of the problem for the astronomy community at the moment, and I'm sure you're aware of that. But a rather interesting question that came up from Mike Peel. Have you looked at all at the transmissions from the LeoLabs radars that potentially bounce off, you know, satellites in low Earth orbit are an issue for the astronomy community?
No. No, Mike. So we have a fence that's 75, yards away from us. We're already the energy is down low. We have a very low power comparison to the space fence that the U.S. government put in Quad. We built it so that we could build lots of them. So the power is not really very high at all. We just have exquisite phased array beam tracking and mathematical algorithms. So almost any tracking radar and definitely it's like at least an order of magnitude more the Quad space radar. They have much more power. So I will check with my radar guys about that, but I can promise you any tracking radar is putting more energy up into space than our guys are. We just have a cool way of doing it where we don't need as much power.
Yeah, sure. And I don't know if Mike is sort of part of the radio astronomy community, but one of the things that I was intrigued to learn was that the Murchison array in Australia was used for a tracking experiment where they listened for the reflections of just a regular FM radio station in Australia, I think, bouncing off the International Space Station, and were able to track it, using a bistatic technique. And obviously the ISS is the biggest object up there, but I think the concern of the radio astronomy community is that when things like the Square Kilometre Array come online, it's going to be so sensitive that they're going to be able to see terrestrial radio transmissions bouncing off of objects of about 1/2 meter in size, and there's quite a lot up there. So I think that's where some of the concerns come from.
So I tell you, I didn't mean to marginalize the question. You have my email. Give Mike my email, and I will definitely check with our radar guys and make sure that we're not, get an idea about what kind of levels we might be talking about. I think we're okay, but that's a good question. And as I've always said, it's not so much about being right; it's about asking the right question. So Mike might have a great question. I'll raise with the radar guys, the experts. Thank you for that.
Yeah, I think it's an interesting question, but I think the emerging consensus from the radio astronomy community is that it's not just the reflected signals that are a problem. Obviously satellites transmit, and we touched on that earlier in the session, and their direct transmissions, if not well filtered, potentially can get into the radio astronomy bands as well. So we are a potential risk as in the space community of actually corrupting both the optical astronomy environment and the radio astronomy environment with the things that we're doing. And clearly there's a long debate to be had about how to actually manage that sustainably in the future. And hopefully we can, as through this network, help to contribute to trying to keep everybody reasonably happy.
Absolutely. Yeah, no, that's a very interesting question. Good.
Yeah. We're approaching